If you're a developer working in AI, you know the feeling. That soul-crushing error message pops up, and it's that moment you realize your ambition is way bigger than your hardware. But what if the solution isn't a bigger machine? What if it's just a smarter way of thinking? This really gets to the heart of our story. It's a problem voiced by Timothy, a junior engineer. He's built these brilliant, specialized AI models, but he's hit a total wall. He can't get them to work together for one simple reason. They're just too big. So that brings us right to our first section. The bookshelf is full. For developers, this is the dreaded CUDA out-of-memory crisis. It basically means your GPU's memory is, well, it's completely full. No more room. So picture this. Timothy is working with a whole set of these powerful, specialized AI models. Think of one as a researcher, another as a translator, and a third one's a summarizer. Each one is a total expert in its field. But when he tries to run them all on a single GPU, the system just throws its hands up. There's literally no more space. Here's a really simple way to think about it. Imagine each AI model is a massive, leather-bound encyclopedia. The GPU's memory, its VRAM, that's the bookshelf. Now, these books are packed with knowledge, but you can only fit one on the shelf before it starts to buckle under the weight. Okay, so how on earth do we solve this? Well, that brings us to part 2, shrinking the numbers. And this is where we get into the core concept of weight quantization. Weight quantization is the big idea here. At its core, it's a technique to save space. Now, we're not removing any knowledge from the model. We're just changing how that knowledge is stored. We do that by reducing the precision of the millions of tiny numbers, or weights, that make up the model's brain. We kind of call this the precision tax. I mean, look at this. On the left, you've got a number with a ton of decimal places. That's a 16-bit float. And on the right, it's been simplified way down to a 4-bit integer. It's a pretty dramatic simplification, and that's exactly where we save all the space. A great way to visualize this is like turning a super high-res photo into a really clean, sharp sketch. You lose all the microscopic, pixel-level details, sure, but the essential information, the structure of the face, it stays perfectly clear. The core reasoning of the model is totally preserved. But that leads to a pretty obvious question, right? And that brings us to section 3, trimming fat, not muscle. How do we actually do this without, making the model dumber? Exactly. This is the critical concern. If you just blindly round down every single number in this incredibly complex system, isn't there a risk that a tiny error at the beginning snowballs into a massive hallucination at the end? It's a totally valid fear. The answer is this really clever process called post-training quantization, or PTQ. And you should think of it less like rounding and more like surgery. First, you calibrate it by running some sample data through the model. As you're doing that, you identify the most important numbers, the outliers. Then you protect those critical weights, keeping their precision high. And only then do you go in and aggressively compress everything else. Ultimately, it's about trimming the fat, not the muscle. You're intelligently cutting away the parts that take up space, but contribute less, all while preserving the core strength of the model. It's smart. So what does all this smart compression actually get you? Let's talk about the payoff. Section 4, more brains, less space. Here it is. This is the hero number. By moving from those 16-bit weights down to 4-bit weights, you can get a memory footprint reduction of nearly 75%. I mean, that is a staggering efficiency gain. It's not a small tweak. This is a complete game changer. And this chart just drives the point home. On the left, you see the before state. That's one model, and its original high-precision format, taking up almost all the GPU's memory. And on the right, the after. It's the exact same model, but quantized. And look at that. It's now using just a quarter of the space. And what this enables is a fundamental shift in your architecture. You go from a one model, one GPU bottleneck to what's called a multi-tenant architecture. Remember that bookshelf that could only hold one heavy book? Well, now it can comfortably hold 4. 4 specialists all working in parallel on the very same hardware. Okay, let's bring it all home. Section 5, mastering the bits. This is the one key takeaway you really need to remember. So, quick recap. Quantization shrinks models by lowering the precision of their internal numbers. That massively improves your GPU memory efficiency. The smartest way to do it is with post-training quantization, or PTQ, because it protects the most important weights to keep the model accurate. Simple as that. So what happened to Timothy, our engineer from the beginning? His out-of-memory error? It vanished. He successfully deployed his whole team of specialists on that single GPU. He realized he had the same brilliant brain he started with. It was just wearing a much lighter, more efficient suit. And this is the line that just captures the entire principle. A piece of wisdom from his senior colleague, Margaret. When you master the bits, you master the scale. That control over these tiny, fundamental details gives you control over massive, system-level architecture. Which kind of leaves us with one final thought. We often think about building bigger and bigger models. But if this much performance and scale can be unlocked just by being smarter about the bits and the bytes, what does that really mean for the future? If performance is just a matter of bits, what are we going to build next?